So at this stage, we have correspondences between points in the left image and the right image. We want to take each one of these corresponding pairs and use the image coordinates of those points to estimate the three-dimensional coordinates of the point in the scene. And that's what we refer to as computing depth. And we know that that process involves triangulation. So here is a point in the left image, here's the corresponding point in the right image. We essentially want to find the three-dimensional coordinates of the point P in either the left camera coordinate frame or the right camera coordinate frame. It doesn't really matter. So, given the intrinsic parameters which are known to us, the projections of a scene point on the two image planes, image sensors, are given by these two expressions right here. This is the point P in the 3D coordinate frame of the left camera being projected onto the image, perspective projection using the internal parameters onto the image plane. These are your image coordinates, homogeneous coordinates, and a similar equation for the right camera. So we'll call these the left camera imaging equation and the right camera imaging equation. And these matrices we have seen before. This is the intrinsic matrix for the left camera and the intrinsic matrix for the right camera. Both are known to us. What we're trying to find here is using UL and UR, we want to find XL or find XR. It doesn't really matter which coordinate frame we compute the 3D coordinates in. So those are two equations, but we have one more constraint here, which is, remember that we have calibrated our stereo system so we know the translation and rotation between the left and right cameras. So that gives us a coordinate transformation, 3D to 3D, from the right camera coordinate frame to the left camera coordinate frame. So that again gives you a relationship between XR and XL through the known rotation matrix and translation vector. So what we're going to do is, for the left camera imaging equation, we're going to take the right-hand side of this equation and substitute for XL right here. So that gives us this left camera imaging equation. And we keep the right camera imaging equation the same. So this can be rewritten as UL equal to PL. This now becomes a projection matrix, which is the product of this extrinsic matrix and this intrinsic matrix. So we can call that a projection matrix, PL times XR. And in this case, the right camera imaging equation, you essentially have MInt, which is the intrinsic matrix for the right camera. So those are your two equations, which can be written as follows. And remember, so now we have all of this known to us. We don't know XR. Again, in this equation, all of this is known to us. We don't know XR. We can rearrange these two equations to get this system of equations right here. And in this system of equations, note that we have four. If you actually wrote these out, you would get four equations with only three unknowns, XR, YR, and ZR. So that's what we have. We have a matrix here, A, which is a 4 by 3 matrix. It's a known matrix. We have a vector XR, which is of interest to us, 3D coordinates of the point in the scene. That's a 3 by 1, and then you have a known vector 4 by 1 B right here. So this is an overdetermined system of linear equations. We've seen this many times before. We know exactly how to solve this using the pseudo-inverse, and we get a solution for XR. We repeat this for every pair of corresponding points in the left and right image. And then that gives us a complete three-dimensional depth map of the scene. So now we know how to go from arbitrary views to depth maps of the scene through this calibration process. So this technique has a very long history, and it has been used more recently to create some very impressive systems. And one of them is this system called phototourism, which was developed by Snavely. And it's an interesting system because what it does is that it basically goes out to the internet and grabs images of the same site. let's say the Eiffel Tower, takes all the images taken by people of the Eiffel Tower, and we know they are of the Eiffel Tower because they're often tagged as such in photo sharing websites, and then apply this technique of calibration between pairs of these images and use many of these pairs to then come up with a dense depth map of the three-dimensional structure. So you may have two images that cover some part of the monument, but you have two other images that might cover some other part of the monument, and create a very large system which is able to pull in all of this data and use a meta tags information in these images to figure out what the intrinsic parameters for each camera or each image is. Use all of this information to then reconstruct a three-dimensional scene from just these arbitrary views. So here is a reconstruction of St. Peter's Basilica. It uses 1,275 images in this case, and you see get very impressive reconstruction. We started off with a point cloud, and now it's being filled in with some texture. Of course, there are holes here and there, but with the passage of time, you can imagine that more and more people end up contributing more pictures, more detailed pictures, and ultimately, even without knowing where these people were in the scene, when they took the pictures, you're able to reconstruct a single cohesive, detailed depth map of the scene. Here's another example by Furukawa. This is Piazza San Marco in Venice. Again, a very large space, but lots of people visit there and take pictures and share them. So from those shared pictures, in this case, roughly 13,000 images, you're able to reconstruct this kind of a 3D depth map. It's a lot of detail. Of course, again, there's missing information here and there, but if you think about it, these are very intricate scenes, and it's rather remarkable that you're able to, for free, so to speak, essentially use the crowd as your photographer to create all of these images and then use them to reconstruct models. And finally, I do want to mention the work of Li Zhang. This is more related to active illumination methods, which we discussed earlier. We know that stereo, as we discussed in the case of simple stereo, depends on the existence of texture to actually be able to find matches between the two images, correspondences between the two images. You need texture, and you'd love this texture to be unique. So one way to make stereo more robust is to use active illumination when possible. So here's a method where an illumination pattern is being thrown onto the object, and in fact, it isn't a static pattern. The pattern itself changes with time. As the person moves, the pattern's also changing. And it turns out that if you have a spatially varying pattern and one that changes over time, you can make stereo even more robust. And so you can see here the type of information you're able to recover in terms of reconstruction. This is a real-time reconstruction of the face of this person, Li Zhang in this case, and it's being reconstructed with very high accuracy to the point that you can actually do some expression analysis and so on.